Good evening, everyone. We are in the week 11 problem solving session of the NPTEL course, Network Analysis. And week 11 is about two-port network and gyrator. Let me share my screen. Okay, before we go on to week 11, let me just quickly summarize what we have discussed in week 11, week 10. Because week 11 also discusses about two-port network followed by gyrator. So let us just quickly summarize what we have discussed last week before we get into week 11. So in week 10, first, we started with the introduction to two-port network, the voltage polarities as well as the current directions, followed by different parameters. First, we have discussed about the short circuit admittance parameters, which are also called as Y parameters. Then we discussed about the open circuit impedance parameters, which are Z parameters. And then we discussed about the H parameter, which are also called as hybrid parameters, followed by the transmission line parameters or T parameters, or you can also call them ABCD parameters. So we have discussed about how to get these parameters for a given two-port network and how they are defined and what are the conventions and how to get those matrices. Then we have seen the relation between these parameters. So if we are given Y parameters, how to get Z parameters out of it, or if we are given Y parameters, how to get H parameters out of it. So we have discussed how to get the relation between different parameters. Here we have considered two examples. One is the Y and Z parameter relation, and then H and Y parameter relation. Then we have discussed about the reciprocal two-port network. So if a network is said to be reciprocal, what does that mean? And what is the condition that two-port network has to satisfy so that we can say it is reciprocal? So this is the condition that it needs to satisfy. Then only we can say a given two-port network is reciprocal. So for this condition to be satisfied, we got the different relation for all these parameters. So in the case of Y parameters, this is the condition that it needs to be satisfied, y1 equal to y2. Similarly, for the Z parameters, it is the same, z1 equal to z2. Whereas in the case of H parameters, it is h1 equals to minus h2. And in the case of ABCD parameters, it should be AD minus B is equal to 1. Similarly, if a two-port network is said to be symmetric, what is the condition that needs to be satisfied so that we can say a given two-port network is symmetric? So this is the condition. Now, using this condition, we have obtain the result for each of these parameters. So when this any one of these is satisfied, then we can say a given network is said to be symmetric. Then we have started doing problem solving session where we have considered a few problems. So in the first problem, they have asked us to calculate the H parameters. So accordingly, we have calculated the H parameters. The second problem, they have asked us Y parameters as well as Z parameters. So we got Z parameters and we know the relation between Y and Z parameters. Then using that relation, we got the Y parameters as well. And they have also asked whether the network is reciprocal or not. And whatever result we have obtained, using that we have shown that it is not symmetric, but yes, reciprocal. So in the last week, we have discussed about the basic introduction of two-port network as well as the parameters that we can obtain from the two-port network. But today we will be discussing about different possibility of connection of two-port networks. Say if multiple two-port networks are connected in series or in parallel or in cascaded form. So how the parameters will be look like for the entire two-port network, as well as we'll discuss about the two-port network like a transformer, whether it is a two-port network or how to represent a transformer in using the two-port network concept. Then and then we'll discuss about gyrator, only a few aspects, mainly some basic understanding about the gyrator. So today I will start with the series connection of two-port network. So I hope you can see my screen. So first one is the series connection of two-port network. So when we say series connection of two-port network, we can consider n number of two-port networks and they're connected in series. But for the ease of understanding, we'll consider two-port network and we'll connect them in series. So when we say series, it means the input side, input port, it is connected in series as well as the output port, which is also connected in series. Okay. Now let us quickly draw the diagram and we'll see. So this is our network one, and similarly we'll consider network two. So I'm calling this network one N1 and this is network two N2. And each of them are two-port network. So here we have one two-port network for the network N1. Similarly, N2 we have another two-port network. Okay. Now we are connecting them in series. So when first of all, let me quickly draw the voltage polarities. So plus minus V1 and I1. Here also plus minus V2, and kindly see that we are following the same convention that we have discussed in the previous class. So this is V1 dash, I1 dash, and plus minus V2 dash and I2 dash. Now we are connecting them in series. So I'll connect this with this, and this is our overall two port. Okay. Similarly, here also I'll connect this like this, and this is our two port. Now I can see the overall two port network considering two ports on the left hand side and two ports on the right hand side. So this is our port 1 and this is our port 2. Okay. So now for this entire two port network, what are the parameters? So when we say series connected, we'll first do with the Z parameters. So why Z parameters that we'll discuss slowly, but let us start with the network N1. So network N1, say the Z parameters are Z11, Z12, Z21, Z22. So if we take that, we have V1, V2, we know about Z parameters, right? So V1, V2 is equals to Z11, Z12, Z21, Z22 into I1, I2, right? Now, this is for network N1. Now we'll do the same for network N2. Sorry, network N2. Oh, let me just write it on the top just to save some space. Okay. So now network N2 we have V1 dash, V2 dash. Here we have Z11 dash, Z12 dash, Z21 dash, Z22 dash into I1 dash, I2 dash. Right. So we have this kind of setup over here. But if you uh, observe, we can say this current I1 is flowing into the next two port network N2. So we can say that here we have I1 is equals to I1 dash and I2 is equals to I2 dash because the same current is flowing in the other network also because they are connected in series. Current is being shared. Current is same. So we have I1 equals to I1 dash and I2 is equals to I2 dash. So I can write instead of this portion, I can write this as I1, I2. Both are same. So now what I'll do, say this is my equation one and this is my equation two. Now I'll add both equation one as well as equation two. And kindly note, on the RHS side, both are having I1 and I2. So we can take common these and we can directly add these matrices. So now I will get, so now 1 plus 2 gives, what it will give? It will give something like this. V1 plus V1 dash, V2 plus V2 dash is equals to, now we have this Z parameter, Z11 plus Z11 dash, Z12 plus Z12 dash, Z21 plus Z21 dash, Z22 plus Z22 dash into, we have currents over here, right? I1, I2. So we have I1, I2. Okay, fine. So now if you see, this V1 plus V1 dash is nothing but the polarity at this port. So I can say this plus minus and the voltage is V1 plus V1 dash. Similarly, the voltage here is plus minus V2 plus V2 dash. Okay. If you see the current entering the port 1 is I1 and current entering the port 2 is I2. So the voltages are V1 plus V1 dash, V2 plus V2 dash, and the currents are I1 and I2. So we got in terms of impedance matrix. If you see, it is voltage is equals to impedance matrix into current. So this is basically our impedance matrix. So this is basically our impedance matrix. So now you can see if two networks are connected in series, then the impedance matrix of the overall network is just summation of the impedance matrices of the individual two-port network. So here, as the current is say, we are considering the Z matrix. So on the RHS side, we have currents common term, so we can directly add the matrices. So that's why we have considered the Z matrix because currents are common. That is the main reason we have considered Z matrix. Similarly, you can do for H parameters, Y parameters, but there it may not be straightforward as we got over here. So because they're connected in series, currents are common, and that's why Z parameters are simple to calculate. So anytime someone asks you to work on multiple two-port networks connected in series, we can deal with the Z parameters, and later you can convert them into Y parameters because we know the relation between Z and Y, Z and H, Z and T parameters. So first we'll start with the Z parameters, and then we can complete Z parameters calculation, and then we can go into the other parameters calculation. So now if you want to summarize, so we can say that the impedance matrix of the overall two-port network when they're connected in series is just the summation of the impedance matrices of the individual two-port networks. So so we can write impedance matrix the impedance matrix of a series connected of a series connected two-port network is the summation of the impedance matrices of the individual two-port networks. Of the individual two-port networks. Yes. So this is it. So when there is a series connection of two-port network, then we'll calculate the Z parameters, and then we can get the overall impedance matrix of the series connected two-port network is just the summation of the impedance matrices of the individual two-port network. So now, in the same way, we can do for parallel connection of two-port network as well. So let us quickly do for parallel connection as well. So here we have input port parallel because it is parallel connection. We have parallel connection both at the input as well as the output port. Input port and output port. This is also parallel. So let us take another example of two-port networks connected in parallel. So let me just quickly draw. So this is our network N1 and this is our network N2. Okay. So this is network N1. This is network N2. And let us consider the two ports here. So now when we say they are connected in parallel, which means they are connected something like this. So this is connected over here and this is connected over here. So these are the new two ports. Similarly, these are connected like this. Sorry, this is connected with this, and this is sorry, this is connected something like this, and these are the new two ports. So similarly, we can consider these are the new two ports of this network. All right. So now this is our new port input for say port 1 and this is port 2. Okay, let us consider the voltages in the same V1, V2, I1, I2, V1 dash, I1 dash, V2 dash, I2 dash. Okay, so if you see in our previous case, as the currents are same, on the RHS side, currents are common, so we could directly add the Z matrices. Whereas in this case, the voltages are same. If you see here we have here here we have V1 equal to V1 dash and V2 is equals to V2 dash. Okay. So now we want the voltages to be on the right hand side. So we can also simply add in this case also. So in what parameters voltages are on the right hand side? If you remember, Y parameters. So we'll start with the network N1. What are the Y parameters? So on the LHS side, we have I1, I2 equals to Y11, Y12, Y21, Y22 into V1, V2. Now we'll go to network N2. Okay, so here also we have the same way I1 dash, I2 dash equals to Y11 dash, Y12 dash, Y21 dash, Y22 dash. Okay, into V1 dash and V2 dash. Okay, now similarly, if you see here, we have replaced this I1, I2 dash with I1, I2. The same thing we'll do here. We'll replace this V1 V2 dash with V1 V2. Now if you see, we can add these two equations again. So let us name this equation as equation 1 and this as equation 2. Now we'll do equation 1 plus equation 2. So equation 1 plus 2 gives, what does it give? We'll, on the LHS side, we have I1 plus I1 dash, I2 plus I2 dash. On the RHS side, we have V1 and V2. So let me just quickly write that expression. So we have I1 plus I1 dash, I2 plus I2 dash is equal to, we have Y11 plus Y11 dash, Y12 plus Y12 dash, Y21 plus Y21 dash, Y22 plus Y22 dash. Okay. Into, we have V1, V2. So this is the admittance matrix. Previously we got impedance matrix. So now in this case, we got admittance matrix. Alright. So what we have done, because the voltages are same in this case, we have seen that if we write in such a way or using that parameters which have voltages on the RHS side, we can simply add just like what we have done in the earlier case. So in the earlier case, currents are same, so current should be on the RHS side. So we have used Z parameters. Whereas in the case of parallel connection, we wanted voltages to be on the RHS side. So we have used Y parameters. So now here, the entire logic remains same. So here, the admittance matrix, instead of impedance matrix, we have admittance matrix. So I'll just erase it and I'll just modify it. So here we have, instead of the impedance matrix, we have admittance matrix. So the the admittance matrix of a parallel connector. So previously it was series connected. Now it is parallel connected two-port network is the summation of the admittance matrices of the individual two-port network. So let me just quickly erase this. So this is the admittance matrices of the individual two-port networks. So if it is connected in series, then the easiest way to calculate are the Z parameters. So similarly, just okay. Whereas in the case of parallel connected parallel connected two-port network, the easiest way to obtain any parameter is the impedance parameter, because we have seen the voltages are same. So that's why we are calculating the admittance parameters. And one more thing, let me just write the voltage polarity. So this is a plus minus. We have here V1. This is plus minus. We have here V2. But if you see, the current is I1 plus I1 dash here, and here the current is I2 plus I2 dash, which is also what we have obtained in the this matrix over here. So this is one important thing about series connected as well as parallelly connected two-port network. And now we are moving into another important aspect, which is cascaded two-port network. So what happens when two-port networks are connected in cascade? Cascaded means one input of port one is so output of port one is the input of port two. So let me just quickly draw. You have cascaded two-port network. Cascaded two-port network. Oh, so let me quickly draw. So here we have network N1. Here we have network N2. So this is our network N1. This is our network N2. So let me quickly draw this. This is directly connected. So the output of N1 is the input of N2. Okay. Let me quickly write the polarities. Say this is V1 and the current is I1. And here, kindly check. I am not changing the polarity or any direction of the currents. Okay. So now here let us take V1 dash and say the current is I1 dash. And here the polarity is say V2 dash and the current is I2 dash. So I'm considering in the same exact way. Now the question is, if I consider this as my new two-port network with this being port 1 and this being port 2. So how will my parameters look like? So that is the question. So in the series connected, currents are same. In parallel connected, voltages are same. But here what is same? So one thing is the output port of port 1 or two-port network 1 is same as the input port of network 2. So we need to use those parameters which gives us the relation between input and output parameters. So which parameters gives that does that job? ABCD parameters or T parameters. So transmission line parameters, which is also why they are called transmission line parameters, because they are used in transmission line application and where there are multiple transmission line connected, and they use those parameters in that application. So that's why they're also named after it. So let us consider the T parameters or ABCD parameters for network 1 and network 2. So network 1, the input V1 I1 is equal to, we have A, B, C, D, right? Into V2 minus I2. We have to be careful because it's a load. So minus I2. It should be considered in the other direction because we are considering as if it is giving to the load. So we have already discussed this in the last week. If you have any queries, you can go through that. So now N2, we have V2 I2 dash equal to A dash, B dash, C dash, D dash into IV1. Sorry, I think I have made one mistake. So this should be V1 dash I1 dash. Okay, these are the input, right? So V1 dash I1 dash, and this will be V2 dash I2 dash. Okay. Now from this uh, interconnection between this, we can say that V1 dash equal to V2 and I1 dash equal to minus I2. So we have, so here, uh, let me use this. So here V1 dash equal to V2 and I1 dash equal to minus I2, because that is what is coming from the connection itself, because they are connected in such a way that this condition is coming into picture. So now if you see this and this becomes same. So now you substitute this for here. So we'll get ABCD into A dash B dash C dash D dash. So now we'll get, therefore, now we'll get the input voltage current and this output voltage current relation. So let me just quickly write. Therefore, we will get V1 I1 equal to A, B, C, D into A dash, B dash, C dash D dash into the output parameters which are V2 and uh, there is another slight mistake here. This should be minus I2 dash according to our convention. So this is minus I2 dash. So we'll write down V2 and minus I2 dash. So now this will become our new ABCD matrix for the entire port. So this is our ABCD matrix. Okay, so now let us just quickly summarize what we have discussed in cascaded two-port network. So there are two-port networks which are connected in a cascaded way. So the output of port one is the input of port two. Output of network one is the input of the network two. So here we have considered ABCD because it's the relation between input and output parameters or output voltages and current. So we have used that, and then we have substituted it. Then we got that the ABCD matrix of the entire cascaded two-port network is just the product of the ABCD matrices of the individual two-port network. So we'll get the similar thing. So here it is summation, there it is multiplication. Is product. So if we write that, so instead of ABCD, we'll have the ABCD matrix. So let me just modify. So the ABCD matrix of cascaded. So this will I'll do and I'll do. Okay, cascaded. Okay, cascaded two-port network is not summation but product of the ABCD matrices. So product of the ABCD matrices of the individual two-port network. So this is one very crucial uh, like result which is used in many wide applications. So when there are multiple two-port networks which are cascaded, then the ABCD matrices it will be product of individual ABCD matrices. So this is one very crucial result. So yeah, so this completes our two-port network different combination of correction of two-port network. Now we'll move on to one example where we consider ideal transformer and then we'll consider uh, ideal transformer as a two-port network. So let me write it. So this is ideal transformer as a two-port network. So we have ideal transformer as a two-port network. So let us consider one ideal transformer. Okay, so first let me quickly draw the ideal transformer. This is the ideal transformer with the dot convention. And for ideal transformer, say if this is V1, this is V2, and we'll consider I1 here, I2 here. But in our two-port network, I2 is in the other direction. But here we are considering in this direction. And for this polarity also, we can write the matrices equation and everything because we know that this is the direction of current in a transformer. So let us consider this ratio as N1 is to N2. Then we know that V1 by V2 equal to N1 by N2, right? So let N1 by N2 to be a matrix A. So now we can get V1 equals to, or let me use a different color. We will get V1 equal to A into V2, right? So we are getting V1 is equals to A into V2. Similarly, we can get N1 I1 equal to N2 into I2. That implies, now say if we want I2 in terms of I1, I2 equal to N1 by N2 into I1. So I2 is equal to A into I1. So now we got V1 and I2 in terms of say V2 and I1. So what parameters we'll be using? H parameters. You know H parameters, it is the relation between V1 I2 and I1 V2. So let us do the same. So now let us take H parameters. Okay. So now we are considering H parameters. So in the H parameters, what are there on the LHS side? We have V1 as well as I2, right? So let us take the V1 and I2. And we have H11, H12, etc., into V2, sorry, I2, or I1, and V2. Oh, now here, what values we have? We have V1 is equals to A into V2. So 0, A, and I2 equal to AI1, A and 0. So these are the H matrix that we are getting, or the H parameters. Similarly, I can get the relation between V1 I1 as well as V2 I2. So this also can be written as I1 equal to 1 by A into I2, right? So now I can use the T parameters, and then I can get another relation between V1 I1 as well as V2 I2. So now if you see I2 here, I2 is considered as if it is the load current. So we'll quickly write this. So now ABCD parameters or T parameters. All right. So in the case of T parameters, we have, what do we have here? Here we have V1 I1 is equals to the ABCD matrices into V2 as well as I2. So now if you see, we have V1 equal to AV2. So AV2 0 I2, and I1 equal to 1 by AI2. So 0 1 by 1. So now this becomes our this becomes our H matrix, and this becomes our ABCD matrix. All right. So uh, for a given ideal transformer, here we are considering only ideal transformer. We can get the relation between the voltages and currents. And here we have considered H parameters as well as T parameters. And these are the matrices that we have obtained. So now let me ask you one question. So if I connect a load over here, what is the impedance seen by, or seen from this port? So what I mean to say is, we have the connection like this. Say there is a load connected over here. So that this is our ZL and this is the polarity. And say this is my plus V1 This is I1, this is I2, and this is plus minus V2. Okay. So now we want what is the impedance when we look from here. So when we look from here, so what is the impedance? Sorry, I think I should draw it the other way. So when we are looking from this side, what is the impedance? So that is what we are asking. So basically we want V1 by I1. So I want basically what V1 by I1. V1 by I1 equal to how much? So they have given say A is to 1. So we'll use this. What is V1? V1 is A V2. V1 is A V2. And I1 is what? I1 by A into I2. So this is A square into V2 by I2. And V2 by I2 is what? ZL. So it is A square into ZL. So the input impedance, if I name it as Z in, we have Z in is equal to A square into ZL. So this you already know in your earlier course, electrical technology ET or whatever undergraduate course you have done. When you are bringing the impedance onto the other side, you should multiply by the square of the turns ratio. So which is also what is happening over here. So the same we got over here. So it is A square into ZL. So yeah, this is how the input impedance will look like if there is one transformer. So now I'll ask you another question. What if there are two transformer cascaded, connected in cascaded form, and then we have impedance at the output side? What is the impedance looked at the input side? Okay. So we have something like this. And here we have another transformer. They are basically connected in cascaded setup. And here we have load impedance ZL. So now basically what we are saying is, say this is A1 is to 1 and this is A2 is to 1. Say this is plus minus V1, I1, I2, V2, V1 dash, and say this is I1 dash, and this is I2 dash plus minus V2 dash. So now basically what happens? What is the impedance seen from this side? If I look from this side, so what is the input impedance? So that is the question. So in order to answer this question, I can say these are cascaded, connected in like a cascaded form. So it's a cascaded two-port network. So these can be modified to something like this. One, so here we have ZL and say the new turns ratio is A is to 1. Okay. And this is the dot convention. So now basically we are looking from this side and we are getting the impedance, right? So basically I have considered this entire thing as a single transformer. So as they're connected in cascaded format, what product I can consider? I can consider the product of the ABCD parameters. So I'll consider this A001 by A and then I'll do. So now this is what? So this is my plus minus V1 and this is my I1, right? And this is my plus minus V2 dash and this is I2 dash. So my V1 I1 is equal to product of the ABCD matrix, which is the important term over here. So A001 by A. So we have A1 0 0 1 by A1 multiplied by A2 0 0 1 by A2. Okay, multiplied by V2 dash and I2 dash. Okay, so if I simplify this, or if you do the matrix multiplication, you will get A1 A2 0 0 1 by A1 A2. So as if it can be replaced by a transformer having this ABCD matrix where A, the new A, is A1 A2. So which is what we got here. So A equal to A1 A2. So this is our new A. So if multiple transformers are connected, the net turns ratio is the product of the individual turns ratio. So now if I want the input impedance, it should be turns ratio square into Zn, right? So now I will get Z in equal to A1 A2 whole square into Zn. Okay. So this is our translation. So with this, we have actually completed the two-port network, but we'll go into Gyrator, which is again an application, just like ideal transformer. So today we have discussed about series connection of two-port network. So just to summarize what we have discussed today, we have discussed the series connection of two-port network, where we have considered two-port network which are connected in series, and we have got the overall impedance matrix, and we have realized got to know that the impedance matrix of the overall series connected two-port network is the summation of the impedance matrices of the individual two-port networks. Similarly, for the parallel connection of two-port network, where two two-port networks are connected in parallel, we have seen the admittance matrix of the overall parallel connected two-port network is just a summation of the admittance matrices of the individual two-port networks. Similarly, when there are two cascaded two-port networks, it is the ABCD matrix. So the ABCD matrix of the cascaded two-port network is the product of the ABCD matrices of the individual two-port. And then if we consider ideal transformer as a two-port network, then we have seen uh, the H matrix as well as ABCD matrix, and we have seen that if multiple such cascaded uh, transformers are considered, then the overall turns ratio is the product of the individual turns ratio. So in the next subsequent discussion, we'll discuss about the gyrator circuit. So we'll discuss what is gyrator circuit and how we can apply the two-port network concept to gyrator circuit. Okay, now let us talk about the gyrator circuit. Gyrator circuit is an application of two-port network, but we'll see like what is gyrator and how two-port network can be applied to gyrator, etc., etc. So now the topic is gyrator. So gyrator is a two-port network that satisfies one certain type of condition. Okay, we'll check the details of it. Say this is our network, two-port network. Okay, so let us consider the voltages plus minus V1 and current is I1, and this is plus minus V2 and the current is I2. Okay, uh, so the hello, hello. Okay, so the condition that generator needs to satisfy is V1 is equals to minus K into I2. So the condition that it needs to satisfy is V1 is equals to minus K into I2 and V2 equal to K into I1. So if this is satisfied by a two-port network, then or we can say a gyrator is a two-port network, it satisfies this condition. Okay. Here K is called gyrator constant or resistance because K is having the dimension of a resistance. So here K is equal to gyrator constant or gyrator resistance? Gyrator constant or gyrator resistance. Oh, but okay, so this is just a basic definition of the functionalities of the gyrator. But, okay, let it be. Now we'll consider another quick example where on this RHS side we will be connecting one inductor. Okay. Now we'll ask what is the voltage or what is the impedance seen at this port. So what is the impedance seen at this port? Okay. So if there is an inductor of inductance L, we know V is equal to L di by dt. So V2 is equals to L into di2 by dt. Right. So now we'll substitute V2 as well as I2. V2 is what? V2 is K into I1. So K into I1 is equals to L into I2. I2 is what? Minus 1 by K into V1. So minus 1 by K. And also L is equals to, sorry, V2 equal to L di2 by dt, and I2 is in the opposite direction. So there will be one minus sign here, minus di2 by dt. So that minus will be over here. So minus L into minus 1 by K into V1, right? So dV1 by dt. So into dV1 by dt. So now I can write the equation as I1 equal to L by K square into dV1 by dt. So this is what? This is an equation of a capacitor, right? So this is the equation of a capacitor dynamics as if there is a capacitor connected at the input port. So if we are connecting an inductor at the output port, it looks like as if there is a capacitance connected at the input port with the capacitance value C equal to L by K square. Okay. So this is one functionality of the generator. So similarly, if I connect a capacitor over here, and if I look at the input port, it looks like as if there is an inductor connected at the input port. So we can uh, use this application to emulate the inductors without using inductor. So if in any circuit we need inductor, we can connect this circuit with that capacitor so that it will act like an inductor without actually using any inductor. So this is just a basic understanding about the generator circuit. Got it? So now, if I connect two such generators in again cascaded, then how will I get the overall relationship between the input as well as the output? So further to be clarified, first we need to get the ABCD parameters, right? Because when they are cascaded, we'll multiply the ABCD parameters directly. So let us calculate the ABCD parameters. Okay. Then in the ABCD parameters, what are there in on the LHS side and RHS side? V1, I1, and V2, I2. I2 direction may be different, but here we are considering in whatever direction we can. Or you can also consider minus I2. So V1, I1, V2 minus I2, because there is already a minus sign here. So V1, I1 equal to the matrix ABCD matrix into V2 minus I2. Okay. So V1 is what? V1 equal to minus K into I2. Sorry, this is minus K into I2, right? So we have 0 K. And I1 in terms of I1 is V2 by K, right? So this is 1 by K and this is 0. Okay. So this is the ABCD matrix of a gyrator. Got it? Okay. Now, if I connect two such gyrator circuit in cascaded format, so I can maybe go back here and then I can get this picture cascaded two potential. Let me just copy paste it here. So this is cascaded gyrator. So cascaded gyrator. Okay. So it is a cascaded gyrator circuit. So now I need to get the relation between V2 I2 dash and V1 I1. So I know that the overall ABCD matrix is the product of the individual ABCD matrix. So I can get the overall ABCD. Say we have input V1 I1. Then the ABCD matrix is the product of individual matrix. So say here the gain is K1, or maybe let me use a different color so it is visible. So let me use the green color. Say the gyrator constant is K1 here and K2 here. So I'll multiply to 0 K1, 1 by K1 0. So we have 0 K1, 1 by K1 0 into 0 K2, 1 by K2 0 into, sorry, multiplied by V2 I2. Okay. So now this can be given as, so 0 K1 into this. So it will be K1 by K2 and then 0 and then 0 and then K2 by K1. Okay. Okay. So how does this look familiar to you? If we see, if you go back to the transformer is having an ABCD matrix of A0, 0, 1 by A. And here also it is similar, right? If this is A, this is 1 by A. So as if this is having a transformer with trans ratio, as if there is a transformer trans ratio A equal to A1 by K. So if there are two gyrator circuits connected in cascaded form, then it works like a transformer, and the trans ratio A is given by K1 by K2, which whereas K1 is the gyrator constant of the first two-port network, and K2 is the gyrator constant of the second two-port network. Got it? So before, like in this week, whatever is discussed by sir in the lectures is up to this, and further aspects of gyrator will be discussed in the upcoming week. So we'll discuss this the further topics in the next week problem solving session. But this week we'll end our technical discussion here, and then we'll move on to the problem solving session. Okay. So before we go into the problem solving session, let me just summarize what we have discussed. Brief. So first there is this multiple or different connections of two-port network where we have considered series, parallel, cascaded. In the case of series connection, the input and output ports are connected in series, and here if we use Z parameters, then we can get the easiest way to get the relation between the voltages and currents. So the input impedance, the impedance matrix of a series connected two-port network is the summation of the impedance matrices of the individual two-port network. Similarly, if we consider parallel connection, where the input port and output port are connected in parallel, we can get the admittance matrix or the overall network as the summation of the admittance matrix of the individual two port. If they are connected in cascaded two port network, which means the output port of the network 1 is the input port of the network N2, or the second network. In this case, we'll get the ABCD matrix of the cascaded two-port network is the product of the ABCD matrices of the individual two-port network. Then we have seen the ideal transformer as a two-port network. We got the H parameters, T parameters, and we have seen if they're connected in cascaded. Then the translation will be the product of the individual translation. And from there we can get the input impedance if there is any if there is any load connected at the output terminal. Then we discussed something called gyrator, whereas something called gyrator, and gyrator is a two-port network which satisfies this condition where K is the gyrator constant of gyrator resistance. Then we have discussed a cascaded two-port network. But before that, we have also discussed if there is any inductor connected over here, the input impedance here will be looking like a capacitance and vice versa. Then we have discussed a cascaded gyrator. So if two gyrators are connected in a cascaded form, then it works like a transformer with the turns ratio K1 to K. So now we'll move on to the problem solving session, and we'll solve few problems quickly. Okay, so let me quickly go to one of the assignment level. Okay, so we'll solve this question. Okay, so this is our problem. So in the problem one, they have given one two-port network, and they have connected some resistors and voltage sources at both the terminals, and they're asking what is I1 and what is I2. Okay, okay, fine. Let it be. First, we'll go one by one. So first, for any given question, we have to take down the data what they have given and then see what they are asking, so that we can do without any confusion and without any mistakes. So this is our problem one. So they have given the Z parameters, which is the relation between V1, V2 and I1, I2. So I can write. So let me just write V1, V2 equal to 20, 35, 35, 50 into I1, I2. Right. So we'll get two equations. One is V1 equal to 20 I1 plus 35 I2, and V2 equals to 35 I1 plus 50 I2. Okay. So let it be our equation one, equation two. Now from this circuit here, this circuit, I can apply KVL here and also KVL here. So we'll get 20 minus, let me use a different color. We'll get 20 minus 10 I1 equals to V1, and V2 is equals to 20 I2 or minus 20 I2, minus 20 I2, because if you see the current direction is in the other way, and V2 equal to minus 20 I2. So this is our V1, V2 in terms of I1, I2. So substitute this in these two equations. Okay. Then what we will be getting? So first of all, V1. So first equation. So equation one will turn out to be V1 is what? 20 minus 10 I1 equals to 20 I1 plus 35 I2. That implies 30 I1 plus 35 I2 equals to 20. So this is our equation 3. Now equation 2 will become V2 minus 20 I2 minus 20 I2, sorry, minus 20 I2 is equals to 35 I1 plus 50 I2. Then if you bring 50 I to this side, we'll get minus 70 I2 equal to 35 I1. That equals I1 equals to minus 2 I2. And this will be our second equation. So equation 4. So now if we substitute this equation 4 in this expression, we'll get I1 as well as I2. So from equation 1, equation 3 and 4. So from equation 3 and 4, you will get I1 and I2. And if you calculate, you will get something like this. So you will be getting I1 as 1.6 ampere and I2 as minus 0.8 ampere. Cool. So in the given problem, they have given the Z parameters of this two-port network, and they have connected a voltage and voltage source and resistor at port 1 and resistor at the port 2, and they're asking what is I1 and I2. So from the given Z parameters, we have written down the equations that we have, and then there are four unknowns: V1, V2, I1, and I2. But with the with this kind of setup, with this kind of setup, we know or we can get the relation between V1 in terms of I1, and here also we can get V2 in terms of I2. So we'll get four equations, four unknowns. So if we substitute this V1 and V2 in these two equations, we'll get two equations, two unknowns in terms, mainly two equations in terms of I1 and I2. So we can solve for I1 and I2, and we can get I1 and I2. So if we go back here, so I1 is how much? 1.6 amperes, and I2 is how much? Minus 0.8 amperes. So careful with the minus sign. And yes, and then we'll be getting the I1 and I2. So I hope this question is clear. So this is our problem one, simple and straightforward. Now we'll go to problem two, problem number two. So we'll solve this question. Let me just take a screenshot of this. Okay, so let us read the question. So they're asking for the inner port, Z inner is 50, 80, 60, 70, and they have connected some resistance at the output, and they're asking what is the Z outer or the uh, parameters of this overall two-port network. Okay. So first, again, we'll write the equations that we have over here, and then we'll substitute this V1 in terms of V1 dash, or we'll try to manipulate it to get in the way we want. So this is our problem two. Okay. So first of all, they whatever they have given. So we'll write this. So let me just copy paste this. Take it to our side. So basically, this is our Z input, right? But the values are different slightly. Let us arrange this. So the values they have given are 50, 80, 60, 70. And this is Z input. So now, if we apply KVL in this equation, just in the same way. So if we apply KVL in this equation or in this loop, we'll get V1 minus, and again the current direction is something like this, and there are something like this. So we'll get V1 minus 10 I1 minus V1 minus 20 I1 equals to 0. So you will get something like this. We will get V1 equal to V1, sorry, this is V1 dash. V1 dash equal to V1 plus 30 I1. Alright. And This is our equation of chord. Now, if we apply the KVL in this loop, in this branch, basically, then what we will be getting? We will be getting something like this. V2 dash is equal to, or V2 dash minus 30I2 minus V2 minus 40I2 equals to 0. So you will get V2 dash is equal to V1 or sorry V2 plus 70I2, and this is our equation 3. Okay. So now if we take this expression, Control C. So from here I'll get V1 and V2 in terms of I1 and I2, right? So I'll get something like this. I'll be getting V1 equal to 50 I1 plus 80 I2, and V2 is equals to 60 I1 plus 70 I2. So now substitute this V1 here and substitute this V2 here. So now what will be our new V1 dash V2 dash? Our V1 dash is equals to V1 plus 30 I1. So if we write directly, we will get 80 I1 plus 80 I2. And similarly, we will get V2 dash is equals to 60 I1 plus 70 I2 plus 70 I2, 140 I2. Got it? So this is our outer two port. This is for outer network. So now if we write this in terms of Z parameters, we will get something like this. V1 dash, V2 dash into the Z parameters, which is 80, 80, 60, 140 into I1, I2, and this is Z outer. So if we go back to this question, so they are asking what is the Z outer. So we got Z outer one as 80. So here also it is 80. Z outer two also we got 80. Z outer one two, and then Z outer two one is 60, 60, and Z outer two two is 140. So it is also 140, and it is matched. So basically these problems are very simple. So we are just writing the equations what they are giving, and then we are just manipulating it a little bit just to get what they have asked in the question. So here they have given the inner two-port network Z parameters, and they are asking the outer two-port network Z parameters. So with the equation or the parameters they have given, first I have written whatever they have given, and we'll be getting these two equations. Then I have applied KVL here, KVL here. So I get V1 dash in terms of V1 I1, V2 dash in terms of V2 I2, and then I have substituted this V1 over here and this V2 over here to get the output, the voltages of the outer two-port network in terms of the currents, because currents will be same for both inner and outer two-port network. So then after getting this equation, we have just written in the way that we want, or in the way that they have asked in the question, which is this Z outer. So this is Z outer 1 1, Z outer 1 2, Z outer 2 1, Z outer 2 2. And here we have 80 80 60 140, which is also matching. And yeah. Now then we'll quickly go to our other question. So in this question, which may look tricky or difficult, but it isn't. So this has actually two parts. In the first part, they're asking the y parameters of this, and then they're asking the y parameters of this. If you see, we know that y parameters of a parallel network are summation of the y parameters of the individual two-port network. So this is our y parameter, say y capital Y1 matrix, and this is also capital Y1 matrix because it is just the same network. So the overall entire Y matrix will be two times individual admittance matrix. So let me just take a screenshot of this and then start solving. So this will be our problem. Okay, so first we have to get the y parameters of the network one and W1. So how we'll get the y parameters? So let me write in this here. I1, I2 is equals to Y11, Y12, Y21, Y22 multiplied by V1, V2. Okay, so first we need to get these individual y parameters. How will I get these parameters? By short circuiting V1 or by short circuiting V2. If I short circuit V2, then I'll get Y1, sorry, Y11 and Y21. Similarly, if I short circuit V1, then I'll get Y12, Y2. So this is how we'll be getting. So first let me short circuit I1 or sorry V2. So we'll short circuit this. So this will get short circuited as if I can remove 0.25. So the network will become something like this. So zero point 0.2 followed by zero point 0.5. So what we are basically doing is we are making V2 to be 0. So now my network is zero point 0.2 and zero point 0.5. So this is our 0.25 and this is our I2. This is our plus minus V1. This is my I1 and this is my zero point 0.2 ohms. So zero point 0.2 parallel 0.25 and divided by, so V1 is equals to Z into I1, right? So basically what we want is I1 in terms of V1 because V2 is 0. I want I1 equals to Y11 into V1. So my Y11 is equals to I1 by V1 and here I1 by V1 is nothing but the admittance. So 0.2 parallel 0.25 and we'll get 7. So Y11 is basically 7. Now I have to calculate I2 in terms of V1. So here what is I2? I2 is minus because the direction is in the other way minus 0.2 by 0.45 or I'll write in simple terms then it will be easy 0.2 by 0.2 plus 0.25 into I1, right? And I1 is how much? 7V1. I1 is equals to 7V1. So into I1 or 7V1. Then you will get I2 by V1, which is Y21. So Y21 is equals to I2 by V1, which is how much? Minus 2. So from here, we got two parameters. Basically, we got Y11 is equals to 7 and Y21 equals to minus 2. Okay. So when I or when we make P2 equals to 0, we get Y11, Y21. So we got this. Now we'll make V1 equals to 0. So then we have 0.5 and 0.25. So now let us make, so the circuit will be same, but it will be from the other way. Let us make V1 is equals to 0. Then we'll have here one resistor, and here we have another resistor. And what are the resistor values? 0.25 and 0.5. This is our 0.5, and this is our 0.25. And this is plus minus V2, and this is I2, and this is I1. So if I calculate I2 by V2, I2 by V2, then it will give Y22. So my Y22 is I2 by V2. I2 by V2, which is 1 by 0.5 parallel 0.25. And if you calculate this, you will be getting 6. Or we can say my I2 is 6 V2. Got it? Now I have to get I1. So I1 is minus 0.25 by 0.5 plus 0.25 into I2, which is 6 V2. That implies now I'll get Y12, which is I1 by V2, which is minus 2, right? Minus 2. So here we got Y11, Y21. Here I got Y22 and Y21. So we got Y22 equals to 6 and Y12 equals to minus 2. Full. Okay. Now we get the Y matrix. So Y and W1. So we'll get Y and W1 is Y11, Y12, Y21, Y22. So Y and W1. So we have Y network 1 is equals to Y11, Y12. So 7 and minus 2. So we have 7 minus 2, 6. So if we have this, then we have Y network 2 is 2 times Y network 1 because they are the same network connected in parallel. So it is just a summation of this or multiplied by 2. So we have 14 minus 4 minus 4, 12. So these are the final matrices that we will be getting using this. So if we have here, so our first value is how much? 7. So it is in between this. And the other one is minus 2. Again, minus 2 followed by 6. So 7 minus 2, 6. And the other one is 14 minus 4, 14 minus 4, minus 4, minus 4, and 12. So all the values are matching and we got all the uh, parameters also. So in this problem, which is somewhat tricky compared to previous problems, which are very straightforward. So in this problem, they have given one network, and for that network, we have to calculate the Y matrix, and then they have connected this network one, two such networks in parallel connection, and they have asked the admittance matrix of the new network. So first, if you have to calculate the Y parameters, we know that we'll short circuit either V2 or V1, and then in this case we'll get two parameters. In this case, we'll get two more parameters. So we have done that, and we have calculated I1 and I2. And kindly make sure your current directions and voltage polarities are proper, else one minus sign will be missing, and you will get a wrong result or wrong answer. So first we have calculated the Y parameters of the given network one, and for the network two, it is just two times because it is the summation of y matrix of this, and these two are same. So it is two times the y matrix of this, which we have done over here, and we directly we got to answer. Okay, so this is our problem three. Now let us go to problem four. So in the problem four, we have something like, okay, so problem four, they are asking. So problem 4, they are asking V2 by V1 when port 2 is open circuited, and minus I2 by I1 when port 2 is short circuited, and impedance seen from port 1 and impedance seen from port 2. And yeah, this is a bit interesting problem and also a little bit lengthy compared to our previous problem. So this will be one interesting problem. So this is our problem 4. So first we have to calculate V2 by V1 when port 2 is open circuit. So port 2 is open circuited and they're asking what is V2 by V1. Okay. So how do we calculate V2 by V1? So let me redraw this circuit, or shall we use this, or let me redraw them. We can use it in the way we want. And this is also 10 ohm. And this is short circuit. Oh, sorry, open circuit. So we'll have something like this. And this is 2 ohm. So first of all, we do not know this voltage, so I am considering this voltage to be some V dash. Okay, we'll first apply uh, KVL or KCL, say KCL. So this is V1, right? So this terminal is V1. So let current direction be like this and like this. So apply KCL at V1 and then we'll apply KCL at V dash. So applying KCL at V1. So KCL at V1. So what we'll get I1 we'll get I1 is equals to we'll get I1 equal to V1 by 10 plus V1 minus V dash by 10. Okay, fine. So this will give us one equation one. Now we'll apply KCL at V dash. Then we'll get V1 minus V dash. V1 minus V dash by 10. Okay. And let us assume this is the current direction here, here, and here. So plus 2I1 equals to V dash by 10. Okay. So this is my V1 and how is my V2? This is my V2, right? So this plus minus, this is my V2. Then we'll get one more condition that V2 is equals to V dash. Okay. Right. Okay. First I will substitute I1 in this equation. So first this I1 over here, I will substitute in this expression and I will replace my V dash with V2. So that implies V1 minus V dash by 10 plus 2 into I1. So 2 V1 by 10 plus 2 into V1 minus V dash by 10 is equals to V dash by 10. So multiply by 10 on all the sets. Here we have V1, 2V1, 2V1. So 5V1 minus 2V dash is equals to V dash. So here V dash, 3 V dash. Are we making any mistake? I think we are making some mistake. So let me quickly check here. So I1 is equals to V1 by 10 plus V1 minus V dash by 10. And here V1 minus V dash by 10 plus 2 times I1 is equals to V dash by 10. So V1 minus V dash by 10. Okay. So this is the mistake. So here there will be another 2 which was missing. So minus 2V dash. Okay. So now here we will have 3V dash instead of 3 we will have 3V dash is equals to V dash. And also V dash is, so we have 5V1 equal to 4V dash, which is equals to 4V2 because V dash is equals to V1. Now we'll get whatever they have asked. So in the problem they have asked AV equal to V2 by V1. So AV is equals to V2 by V1, which is 5 by 4. So that implies AV is equals to 1.25. So we'll see AV is 1.25. It is in this region. Okay, fine. So the first part is done. So in the second part, they're asking minus I2 by I1 when port 2 is short circuited. So port 2, if said port 2 is short circuited, then we'll have this can be removed. So we have 10 ohms here, 10 ohms here, and this 10 ohm can be removed. One 2I1 and one short circuit path. So this 10 ohm I can remove and then I can proceed. So if I redraw the circuit, we will get something like this. So we'll have this 10 ohm and here we'll have this 2I1 and here we have 10 ohm and here we have one short circuit path and this is how is the I2 direction. So this is our I2, this is our 2I1, this is our 10 ohm, this is our 10 ohm and this is plus minus V1 and this is I1. Okay. So again we'll apply KCL. First of all, this is my V1, right? And say this is my ground, then this is also ground. So current is flowing like this and current is flowing like this. So I will get I1 is equals to V1 by 10 plus V1 by 10. Agreed? Because this is V1 by 10 and this is also V1 by 10. So that implies I1 is equals to 0.2 V1. Okay. So we got one expression between or relation between I1 and V1. Okay. Now, if we apply KVL or sorry KCL here at this node, then we will get V1 by 10, V1 by 10 plus 2I1 plus I2 is equals to 0. So 0.1 into V1 and V1 is what? 5 into I1. So V1 by 10 is how much? 0.5, right? So it will be 2.5. So this is V1 is how much? Or V1 is 5I1. So then we'll have zero point 0.5 I1 plus 2 I1 equals to minus I2. And in the question, what they are asking AC, right? AI is minus I2 by I1. So AI, which is minus I2 by I1. So if we do that, we'll get AI is equals to minus 2.5. So this is how we will calculate AI, and that's how we get AI. Okay, so this completes the second part of this problem. And in the third part, they are saying that they have connected a 20 ohm resistor at port 2 when the impedance seen from port 1. What is the impedance seen from port 1? So how do we do this? Okay, so let us first let us see that if we connected a 20 ohm here, then 20 ohm and 10 ohm are in parallel, right? So 10 ohm and 20 ohm in parallel is 20 into 10 by 10 plus 20, which is 20 by 3. So the entire circuit will remain same. Only here there will be 20 by 3 ohm resistance. So let us quickly draw them, or maybe I can copy from here also. You can use that. So we have the circuit, except the part that this is not 10 ohm, this is 20 by 3 because 20 ohm is connected in parallel. So 20 by 3 ohm. Okay. And this V2 can also be removed. So basically, we want what is V1 by I1. Okay. Again, the same way we can do first apply KCL at V1. So you will get I1 is equals to, I1 is equals to V1 by 10 plus V1 minus V dash by 10. So we want in terms of V1 and I1. So from here, you will get 10 I1 is equals to 2 V1 minus V dash. That implies V dash is equals to 2 V1 minus 10 I1. Okay, so this is one equation. Now let us apply KCL at V dash. So KCL at V dash. Then we'll get V1 minus V dash by 10 plus V dash by 20 by 3 plus 2 I1 is equals to 0. So we'll get V1 minus V dash by 10 plus V dash by 10 by 3 plus 2 I1 is equals to 0. So now we will get V dash by 10 plus 2V dash by 10 because this is plus 3, this is minus 1 plus 2I1 is equals to 0. So now substitute this V dash here. Then we will get V dash plus, sorry, V1. Sorry, this is V1, this is V1, this is also V1. So V1, here we have V1, V1 plus 2V dash. So 4V1 minus 20I1 plus, or have we made any mistake? So I think we have made another mistake probably. Let us check. So this is V1. So I1 is equals to V1 by 10 plus V1 minus V dash by 10. So if you multiply by 10, we'll get 10 I1 equal to 2V1 minus V dash. So V dash is equals to 2V1 minus 10 I1. Now if we apply KCL at V dash, we'll have V1 minus V dash by 10. Okay, so there is this minus sign. So this plus this equals to this. So here there is one minus sign which we have. Let me show. So this is minus. So now this will become minus 4, isn't it? So this will become minus 4. Okay. So now let us write this again. So on the LHS side, we have V1 plus 20 I1 equal to 4V dash. And 4V dash is what? 8V1 minus 40 I1. So how much we will be getting? 7V1 is equals to 60 I1. So V1 by I1 is how much? 60 by 7. So it is close to 5 point something, and we'll see whether it is same or not. First, we got this how much? 1.25, and then minus 2.5, 1.25 minus 2.5, and this answer is still wrong. So we'll check when we have made some other mistake. So I1 is equals to V1 by 10 plus V1 minus V dash by 10. Okay. And 10 I1 is equals to 2V1 minus V dash. So V dash is 2V1 minus 10 I1. Okay. Now here we have V1 minus, sorry, this is not 10 by 3, this is 20 by 3. Okay, so this is our another mistake. Right. Okay, let us redo it again. This is equals to 0, and this is not 10 by 3, this is 20 by 3. So we'll have V1 by 10 plus 2I1 is equals to V dash by 10 plus 3V dash by 20, which is equals to 5V dash by 20, isn't it? Yeah. So now if we multiply by 20 on both the sides, we'll have 2V1 plus 40I1 equals to 5V dash. And what is 5V dash? 5V dash is 10V1 minus 10 tens are 100. So 5 tens are 50. This is 50 I1. Okay. Now, if we bring V1 this side and I1 that side, we'll have 8V1 is equals to 90 I1. So V1 by I1 equals to 90 by 8. So it will be 11.25 volts. So let us check 11.25. It is within the range. So yeah, uh, we have made many mistakes because there are no students today. Okay, so this Z input is equals to V1 by I1, which is 11.25 ohms. So we got the input impedance when there is 20 ohm connected at the output. The input impedance is 11.25 ohms. Now, the last part of this question, when there is 20 ohm connected at the input, what is the input seen from the output? So they're asking Z out when there is a 10 ohm connected here. So now you may ask, sir, if 10 ohm is connected here, this parallel, and then this in this series, then this in this parallel. So that is the overall impedance. No, but there is a dependent source, so we cannot actually do like that. So let us do so 10, 10, 10. Let us go to voltage. Because there is a dependent source, it is not so straightforward, and we have to consider. So how much 20 ohm resistor is connected? So this is 20 ohm, this is 10 ohm. Again, there is 10 ohm here, and then 10 ohm, and then here there is 2I1. So this is 20 ohm, 10 ohm, 10 ohm, 10 ohm, 2I1 plus minus V2, and they're asking V2 by I2, so that we'll get the overall impedance. And kindly note that this is the direction of uh, I1. Okay. So let me do one thing. So this is I2 and this is 2I1. So what is the current direction here? It is I2 plus 2I1, isn't it? Right. So this is I2 plus 2I1, and this is our I1. So now we have to again apply KCL over here and then also KCL over here. So first of all, we do not know, we know this voltage V2. So this is my V2. So this is my V2, and say this voltage I don't know. This is our V dash. So apply KCL at V2 and then apply KCL at V dash. Anything we can do. So let us assume this is our current direction, and this is our current direction, and this is our current direction. First we'll apply KCL at V2. KCL at V2. If you apply KCL at V2, current entering is equals to current leaving. So we'll get I2 plus 2I1. Current entering is equals to leaving. V2 minus V dash by 10 plus V dash V2 by 10. Right? Yes. V2 by 10. Okay. So this also can be written as V2 by 5 minus V dash by 10. Or we can say V dash is equals to, if you bring V dash that side and multiply by 10, we'll get 2V2 2V2 then minus 5 2s are 10, right? We are multiplying by 10. So it is 10I2 minus 20I1. Okay. So we got this V dash. Now we'll apply KCL at V dash. So we'll apply KCL at V dash. So first of all, what is I1? I1 is nothing but minus V dash by 20. So here you know another equation. I1 is equals to minus V dash by 20. Okay. Okay. First we'll apply KCL at V dash. So we'll have, okay, then we'll substitute first. Let us simplify everything. So we'll substitute this I1 over here. Okay. So let us take this a bit down. Okay. So now if we substitute that, we will get minus 20 I1. So minus 20 I1 is how much? V dash. So that V dash, if you bring this, we will get 2 V dash is equals to 2V2 minus 10 I2. That implies, sorry. I have made another blender here. So V dash is equals to 2V2 minus 10 I2 minus 20 into I1 is how much? Minus V dash by 20. So 20 get cancelled, minus minus becomes plus, and this V dash and this V dash will get cancelled. So now here we will be getting 2V2 equals to 10I2. 2V2 is equals to 10I2, and now we need Z out is equals to V2 by I2. That implies Z out is equals to 5 ohms. Got it? So we just needed an equation in terms of V2 and I2, and fortunately we got it directly because one of this term got cancelled. So first let me summarize the problem 4, then I'll summarize the entire problem solving session, or maybe the entire today's session. So in problem 4, in this problem, they have asked the voltage gain when port 2 is open circuited, current gain when port 2 short circuited, then the impedance seen from the port 1 when 20 ohm is connected, then impedance seen from port 2 when 20 ohm is connected at port 2. So first they have asked when this is open circuited, what is V2 by V1? So we have applied KCL at V1 and KCL at V dash, and by manipulating that we got the AV. And in the other case, they have short circuited this and they have asked minus I2 by I1. We have applied KVL and KCL, and then we got AI as minus 2.5. Sorry, AI is plus 2.5 because minus is already covered. So this will be plus 2.5. And then they have connected a 20 ohm resistor at the output, and then this becomes 20 by 3. Then they're asking what is the input impedance. So V1 by I1 basically. So V1 by I1 we have calculated, and we got something like this 11.25. In the other case, they have connected 20 ohm here and they're asking V2 by I2. So we have applied KCL at V2, and then I1 is also nothing but minus V dash by 20. Then we have substituted here, and then we directly got it without applying KCL at the other put, and we directly got it. So this is our problem 4. Just to summarize today's session. In today's session, we have started with the two-port network, multiple type of connection of two-port network. So first we have discussed the series connection of two-port network, where we have used the Z parameters, and we got the result that the impedance matrix of the series connected two-port network is the summation of the impedance matrices of the individual two-port network. Then we have discussed the parallel connection of two-port network, and here we have used the Y parameters, and we got the result that the impedance matrix of the parallel connected two-port network is the summation of the admittance matrices of the individual two-port network. Then we went to the cascaded two-port network, where we got another result using the T matrices, that the admittance matrix of a cascaded two-port network is the product of the ABCD matrices of the individual two-port network. Then we have seen how we can represent the ideal transformer as a two-port network. We have represented it using H parameters as well as T parameters. And then we have seen that if we cascade two transformers, then the overall turns ratio is the product of the individual turns ratio of these transformers. Then we have discussed something about generator. The more details will be discussed in the upcoming session. So in this session, we have discussed some brief uh, discussion of the brief understanding about gyrator. Gyrator is a two-port network having these additional conditions. If it satisfies, then it is a gyrator circuit. And for this gyrator circuit, there is a constant called gyrator constant of gyrator resistance K. And the advantage of gyrator is you can emulate a capacitor or inductor using inductor or capacitor. So if I connect a inductor here, the input impedance will be look as if there is a capacitance. Also, if we connect a capacitance here, the input impedance will be like a inductance. And the relation between that capacitor and inductance is given by this expression. And also we have represented it using the T parameters of ABCD parameters. And we have seen that if a two generators are connected in cascaded form, then the overall system is like a transformer with this trans ratio K1 by K2. Then we have solved few problems today. And in the first problem solving session, we have Z parameter related question. We have written the equation and then we have applied here and KVL here and here, and then we got the I1 as well as I2. In the second problem, they have given in the inner Z matrix and they're asking the outer Z matrix. So we have written these two equations and we have applied KVL here to get the outer Z matrix. In the third problem, they're asking Y matrix for this and this. So Y matrix for this is obtained by considering V2 equals to 0 in one case and V1 equals to 0 in the other case. And the Y matrix of this is obtained using the this result where the admittance matrix of the parallel connected two-port network is summation of the admittance matrix of the individual two-port network. So by doing that, we got the overall Y matrix. In the problem 4, they have four subparts. The part 1, they are asking the voltage gain by open circuiting this, and we have solved it using KVL KCL, and we got AV. And then they are asking the current gain minus I2 by short circuiting at the port 2. We have done it, and then we got minus I2 by I1, and we got AI to be 2.5. And in the third part, they have connected 20 ohm at port 2 and they're asking the input impedance. And then we have applied KCL and using that we got Z input to be V1 by 1, which is 11.25. And similarly, in the last part, they have connected 20 ohm here and they're asking the output impedance or V2 by I2. So we have applied KCL and in this case, we got Z output impedance to be 5 ohms. So that is it for today, week 11, and the more details about gyrator and open will be discussed in week 12, which is in the next week. So we are slowly moving towards the end of this session. I hope these videos are helpful and you are watching these videos and you are getting benefit from these videos. And all the best for your assignment, week 11 assignment. And I hope you found this video helpful. See you in the next one. Thank you. Goodbye.